Thanks, folks. Good to be with you today. As Kieran mentioned, my name is Bobby Kubor. I'm a solutions architect at Amazon Web Services. My role revolves around digital innovation, so I work quite closely with our customers on some of their more challenging and difficult problems that often involve emerging technologies to assess or resolve. That typically involves IoT, machine learning, or robotics. So my background is heavily based in software engineering. Over the past 5 years at Amazon, I've been involved in everything from ideation to prototyping. I'm typically neck deep in technology, and my house is a bit of a junkyard for hardware. So hopefully I'll be able to share some of those stories of some of the engagements we've been working on over at AWS. But mainly, when people think of Amazon, they don't necessarily think of cloud computing. They don't necessarily think of the bookstore either. We've moved on since those days, definitely. But this is the main thing that most people think of, which is the online marketplace, where you can purchase a wide variety of products that, most importantly, the part that's highlighted, are delivered in an aggressive time frame. So usually when you place an order, I know at least in Australia, when you place an order, it is scheduled for either same day or next day delivery. Now, to be able to achieve that across a wide variety of products does take a fair amount of automation in the back end. And so this is a drone flyover of one of 200 of our fulfillment centers, some of them robotic. In this case, as you can see here, this one is. These robotic fulfillment centers are over multiple football fields in size. And effectively, when you place an order on the Amazon Marketplace, they come to a facility like this, where traditionally a fulfillment center worker would walk the aisle, would collect your product, put it into a box to mail it out to you. But to be able to meet those aggressive delivery windows, we've been able to accommodate for some automation in the form of these robotic drive units that are able to pick up those shelving units full of products, bring them to the fulfillment center worker where they're able to pluck the product out, put it into a box, and send it off. Now, at last count, there was over 750,000 of these robotic drive units deployed across the multiple fulfillment centers across multiple different regions. So it sort of gives you an idea of the sort of scale that we're operating at there. That's just for those robotic drive units. There's obviously other robotic capabilities such as manipulators within those fulfillment centers as well. So Amazon's not just in the business of building out robotic devices for fulfillment centers. We do have consumer-grade devices as well, in line with the idea of the everyday robot. What you can see here is Astro. Astro is basically the taking a science fiction idea and making it a reality. Astro basically has the ability to navigate your home, has the ability to hear, infer, and understand. It has a screen to provide information. It can talk. It has a telescopic camera. So you can interact with this in your home. It can effectively be deployed as a security guard. It can do patrols. But one of the things that it's used most often for is checking on things at home while you're not there. So maybe you think that you've left the stove on. Maybe you think that you've left the window open. You can get Astro to navigate autonomously to check on those things and provide you a live video feed, or potentially provide you recordings of things that are happening in your home, such as maybe your pet doing certain things. The other capability that one of Amazon's subsidiaries is looking at for the home is the idea of a camera that is able to effectively fly around your house via well-known paths that it has been pre-trained on. So essentially, if your Ring door alarm has gone off, being able to autonomously navigate to the door to see what the cause of that is, or once again being able to navigate to a stove or to an open window to provide you information on whether you've left the stove on, whether you've left the window open. So one thing that we've noticed at Amazon over the years is that developers and organizations want that same level of experience when they're building out their own products, whether that's being able to deploy and manage devices at a massive scale, similar to what we saw in the fulfillment centers with the robotic drive units, whether that's using machine learning capabilities to build intelligent robotic capabilities or intelligent robotic applications, such as what we saw in the fulfillment center, whether it's using computer vision to determine which shelving unit has which product, or even anomalous events that are occurring within conveyor belts. So maybe the vibrations are increasing and it needs proactive maintenance. Or it might even be leveraging large-scale databases or storage for storing transactional information or inventory information. Basically, all of these capabilities that the fulfillment centers are using at Amazon are based off technology that is run on Amazon Web Services, the cloud computing platform. All of those services are available for developers and organizations to be able to leverage today. And so we won't be going through the basics of cloud computing. Certainly, I think most people are well aware of what cloud computing is and how it works. If you are early in your career, certainly it's worth experimenting with if you haven't had the chance to. Ultimately, you navigate to the console, put in a credit card, and suddenly you have access to best-in-breed technology that you can use out of the box. So, certainly worth something taking a look at. But ultimately, when people think of cloud computing, they often think of the fact that there is, yes, available infrastructure that you can use straight away. They think of it as compute, as the underlying hardware. They're not necessarily thinking of the higher level services and capabilities that it provides. So one of the great things as a developer is if you're looking at deploying a capability for your application, let's say that it's a low latency video stream, you're able to deploy that out of the box pretty quickly using an AWS service rather than having to handcraft that yourself using an already well-known pattern. So it removes a lot of that heavy lifting. This slide provides you a bit of an idea of the number of services and capabilities that you can leverage straight away after you sign up and you're within the console. You don't have to wait for anyone to approve your access. You're able to launch capabilities straight away. What we're going to be looking at today is primarily a small subset of those capabilities that are relevant to robotic development. So we're going to be looking at things like how to leverage cloud compute to be able to scale out testing of robotic applications, to be able to perform regression testing and use good development practices. We're going to be looking at how to offload some of the compute that is required for intelligent robotic applications by leveraging machine learning and inference in the cloud. And then finally, we're going to be looking at how to manage over the air across a wide scale of devices, basically robotic software and robotic updates using IoT services. We're going to be looking at this in the frame of the robotic development lifecycle. So usually that's a three-step process. The design and develop, so effectively being able to create good robotic applications through good development practices, being able to test and verify through regression testing, and then finally deploying and updating those devices. We're going to be taking a look at this in line with a number of organizations that have had success using this sort of framework and using these sorts of services. So to begin, we'll start on design and develop. Now, as I mentioned before, there's a number of higher level services that can be used to shortcut the building process for robotic capabilities. One of the main capabilities that most folks are looking for is a low latency video streaming capability that allows them to use it for teleoperation or robotic supervision. So this may seem fairly basic, but there's a lot that goes into requiring a low latency video stream. Things like what sort of connectivity, what sort of connection medium? Are we talking about 5G? Are we talking about Wi-Fi? What sort of signal strength? Are there connectivity black spots? How many viewers? How many cameras? things can start to spiral after a while, and there's a fair amount of configuration required to ensure that you're able to cope with what you need to provision. So a lot of organizations look at leveraging services like WebRTC, a low latency video stream option. It's open source. It can be deployed. It's peer-to-peer. One of the challenges with WebRTC is that there is still infrastructure required, even though it is peer-to-peer, to be able to facilitate the metadata, the connectivity metadata transaction, to be able to establish those connections, to be able to create those streams. In addition to being able to navigate firewalls, network address translations, that sort of thing. So there is the requirement to deploy infrastructure such as stun, turn, and signaling servers. And then you need to be able to harden those to ensure that they're stable, that they scale well, that they're durable. That takes work. That takes effort. It's a known pattern that has been deployed. The fact that you would have to go through that and sit there and hand carve it can take a bit of time and effort. The option is to use Amazon Kinesis Video Streams WebRTC that allows you to deploy that WebRTC capability out of the box without really having to do a lot of configuration. It's a couple of clicks. You get a best practices deployment deployed out of the box. It looks something like this at a high level. So effectively, you've got a robotic device that establishes a connection with Amazon Kinesis Video Streams WebRTC. You've got a user who's either on a browser or a mobile application. They're able to initiate or request a video stream from Kinesis Video Streams WebRTC. It then launches two streams and establishes that both users point to point, or at least the robotic device and the user point to point, where you've got one stream for media, so video streams that could be unidirectional or bidirectional. And then you've got the other stream, which is a data stream. That could be used for teleoperations, for instance. It can be used for a number of different things. We're all pretty familiar with WebRTC. We've actually been using it considerably since COVID-19. It's pretty much the foundation for a lot of our video conferencing software. This sort of gives you an idea of what it looks like in practice. What we've got here is a bit of a demonstration that I put together. It's actually running in my backyard. Of performing computer vision to be able to determine the health of infrastructure assets. So obviously this is a small scale wind farm, and we've got a DJI Tello up in the top left-hand corner that is doing it's autonomously navigating around the turbines. It was actually launched using Alexa, so that started its flight. In the rest of the screen, you can actually see the low latency video stream coming through. It's feeding through to a Grafana dashboard where we're able to record the video, and then we're able to perform analysis post-process. So as the drone lands, we can actually see on the right-hand side, we'll expand that out, and we can see where it's been able to detect healthy blades or unhealthy blades using machine learning. We've been able to draw the appropriate bounding boxes, label each blade appropriately, and provide a confidence score based on that. So when it comes to leveraging that machine learning capability, certainly you have the ability to deploy models down to the edge. As you can imagine, trying to run a model on a Tello, DJI Tello, would be near impossible. So to be able to run that computer vision model, we're actually doing a lot of that in the cloud. To be able to do that, we're using, we like to think of AI services at AWS as a three-tier. The first tier being AI services. These are capabilities that you can leverage using an API out of the box. You don't need to crack open a Jupyter notebook. You don't need to train a model and deploy it. These are capabilities that you can leverage just by invoking an API. So effectively taking a photo, submitting it to an API, and then getting a reply back in JSON form that provides you an understanding of what's in the image, the label, the confidence score, where the bounding box should be drawn. There's a number of those types of capabilities that are provided out of the box, so you don't necessarily need a machine learning background to be able to use. That includes conversational agents based off Alexa. That includes things like text-to-voice capability. Obviously, there are some latency considerations there, right? So if you need to be able to take action within a sub-second latency, then you probably want to deploy the model down to the edge, down to the device. For that, we have the SageMaker ecosystem that really provides an end-to-end capability to build, train, and deploy models. Everything from being able to label your data or being able to distribute the labeling of data, all the way through to optimizing a model and deploying it down to the edge, optimizing it depending on that hardware that you're running. And then finally, if you don't want to deal with the overheads of the ecosystem that are provided for you, if you're a machine learning practitioner and you simply just want to leverage GPUs, CPU, infrastructure, and frameworks out of the box that you're familiar with, you can certainly use that bottom tier as well. So capability for people who have absolutely no machine learning experience to absolute practitioners. So as I mentioned, one of the capabilities that is provided sort of out of the box that you can leverage just by invoking an API is Amazon Recognition. It provides all of these capabilities to you out of the box. So if you provide it a picture or a photo, it will be able to tell you things like what is in there in terms of object, scene, or activity. Whether there's text, it uses OCR to be able to determine that. Whether there's PPE, facial detection and analysis, that sort of thing. We're actually using Amazon Recognition for that previous demo that you saw with the DJI Tello, being able to draw bounding boxes around individual blades. Now, that's a very specific use case, a business use case. So to be able to do that, we're actually using custom labels. What that allows us to do is take a bunch of images. So we've taken a bunch of images of the blades, of the turbines. We've drawn the appropriate bounding boxes around each blade, labeled it healthy or unhealthy, and then press the train button. And that's all you really need to do to perform transfer learning, to be able to build out your custom use cases using Amazon Recognition. So it allows you to detect things that it wouldn't detect out of the box. So one organization that's actually using these sorts of managed AI capabilities is Robot Care System. They've built this robotic walker, which is called Leah, the Lean Empowering Assistant. They essentially this walker has a number of robotic capabilities to assist a senior. So it has the traditional walker elements, but being able to do things like detect obstacles and avoid them, even to be able to autonomously navigate to the person using their wearable so that it comes to them so that they can get up. They wanted to be able to integrate a conversational agent or interface, as well as facial detection. But the compute that's running on that device was fairly restricted. And additionally, they didn't want to build something from scratch. So they were able to use Amazon Recognition to be able to build that face detection capability. And they were able to use Amazon Lex, which is the Alexa conversational agent, to build out a conversational capability or a conversational interface. Now, obviously, there's going to be times when latency is going to be a factor. You don't want to have to wait for a query to go to the cloud and back to determine what to do next. You might need to. It might need to be a split-second decision, and for that, you can certainly build and deploy a model using Amazon SageMaker. This provides, as I mentioned before, an ecosystem that allows you to train. Label data, so you can actually distribute that labeling to an entire team. It provides you an interface that allows people to draw the appropriate bounding boxes and label the data, all the way to outsourcing the labeling of that data, being able to use hosted Jupyter notebooks with built-in algorithms or built-in models for transfer learning, to be able to scale out your training jobs across multiple GPUs, across multiple instances, to be able to speed up training, and then being able to deploy. Sorry, this is probably the next slide since I couldn't see the slide. Being able to then deploy models down to the edge, being able to optimize it, version control it, and then deploy those models down to the edge. And so this sort of gives you an idea of the process involved. So, I mean, the first step is to, and this is for if we were to train a computer vision capability using Boston Dynamics Spot. So we would upload our photo data or our picture data to Amazon S3, an object storage platform. We'd be able to use Amazon SageMaker Ground Truth to be able to label that data appropriately. And then run it through a training job to be able to build out that model. That model would be staged into Amazon SageMaker's model registry where we can version control it appropriately. We can also optimize it for the edge hardware that's it's going to be deployed to, whether that's an ARM processor, x86, Raspberry Pi, Jetson Nano, could be anything. And then we're looking at deploying that model down to the device itself. Now, I'm going to cover AWS IoT Greengrass a bit later on, but for the time being, think of it as a capability that allows you to deploy essentially modular bits of software over the edge down to the device and manage the life cycle of that. From there, we're able to interact with SpotCam, Spot Core AI, and Spot SDK to be able to draw the appropriate bounding boxes and have that appear on Spot Tablet without going to the cloud at all. So to give you an idea of how that would look, this is the view from the Spot Tablet, where we're able to run inference right at the edge there. You can see it's obviously detected the bicycle, and then it's able to detect other forms of transport as well. It's drawing the appropriate bounding box on each frame, and the label and confidence score appropriately. So obviously a much quicker way of being able to get real-time inference. The other use case is really around reinforcement learning. Now, one of the challenges, I guess, with reinforcement learning and running it on your own machine is obviously the ability to scale. It obviously consumes a fair amount of resources to be able to provision a simulation and be able to run an agent within that simulation, continue to get feedback to increase its cumulative reward. And so as a result, we can leverage simulation environments in the cloud and really scale them out. So we can use things like ROS-I to be able to scale out simulations for reinforcement learning, to be able to quickly be able to build out models for all sorts of capabilities. You can actually see on the right-hand side some frames from, or some video from training out our Deep Racer simulations. Is effectively a competition to see who can build the best reinforcement learning model. So being able to scale out our simulations across multiple tracks with different lighting certainly has the ability to speed up that process. And being able to have each simulation have assigned its own compute infrastructure and resources certainly allows for that. So one organization that did use reinforcement learning, they used Kubeflow pipelines on Amazon SageMaker with ROS-I to be able to scale out their simulations for reinforcement learning, is Woodside Energy. They are a oil and gas production company based out of Australia. They have a lot of different remote assets out in the field, whether that's offshore or just remote Australia. A lot of these facilities are unmanned, and that they have hardware that is operational there. If something goes wrong with that hardware, they often need to do a remote shutdown, which usually you'd be able to do by clicking a button in a console. If that fails, they would traditionally need to send someone out in a chopper to be able to effectively press the big red button. Now, that is obviously time consuming, it's expensive. So they looked at building out Ripley, which is this robot that you see here. Ripley is a ClearPath base with just an open source navigation algorithm. It's obviously been able to use that to navigate to the Uruko marker on this water loop that's pumping around. It's just a test water loop. And it's now performing a sequence of actions to be able to shut down that water loop. The manipulation that you're seeing in the arms is actually a manipulation capability that was built with reinforcement learning using SageMaker and Kubeflow pipelines on AWS. So it's actually quite a complex number of movements that it needs to do to turn a bunch of levers and press some buttons to be able to shut it down. But this was built in collaboration with NASA JPL. The same capability that you're seeing here with the arms is additionally in NASA JPL's Robonaut that works on the space station. So once we've built out a capability, we then need to test and verify it. For most of us, this is running ROS launch and hoping for the best. I know that's generally what I do. I'm sitting there watching a gazebo simulation, and hopefully it works. And sometimes it doesn't, and then I sort of go back to building something else out. But for a lot of organizations that have millions of devices in the field, that's probably not going to cut it. The last thing you want is late bug discovery in the field. And so a lot of organizations are starting to move more towards a CI/CD approach for robotic development. So continuous integration, continuous delivery, or deployment. Now, that's pretty commonplace in web applications, in mobile applications. It can be a bit harder to do in robotic applications, mainly due to the testing pillar. When you have to test a web application, it's much easier to automate than having to test multiple different robotic scenarios and multiple different versions of a robotic device. However, we obviously have simulations. Usually if you're just working off your own laptop, you can usually only run one simulation at a time, but obviously with the cloud, you've got the ability to scale. So being able to run multiple simulations in parallel. AWS RoboMaker provides a managed simulation environment that can be invoked via an API to allow you to batch scale your simulations. And around that, you can, those simulations can be high fidelity. They can either be Gazebo, they can be Unreal Engine, they could be Unity. Whatever you want to bring to the table is possible to run in AWS RoboMaker. The good thing about this is because it's all API driven, you can kick off your simulation jobs. You can continue to monitor those simulation jobs, collect that feedback, and build out effectively a traffic light type system in a business intelligence tool that dictates whether those tests were successful or not. And so what that would potentially look like from a development perspective, if you're a developer, you would be doing development on your own local workspace. You would be testing that out probably in your own local workspace as well for that feature that you're building. You'd be pushing into Git. This assumes that you're using Git for version control. And then we're assuming that we're using AWS Code Pipeline for the orchestration of our build. That code would clone down into AWS Code Build to effectively be built, whether that's Catkin Make or Colcon Build, to build out those ROS packages. Then that would be packaged into a container image that would be deployed into Amazon's Elastic Container repository, very similar to Docker Hub. From there, we would then launch a number of simulations in parallel. These simulations could test out different scenarios or different versions of a robotic device. And we're using AWS step functions to manage those simulations, the life cycle of those simulations, spitting out the results into Amazon S3, our object storage platform, where we're then able to query those results using Amazon QuickSight, which is our business intelligence tool. So we can effectively build like a traffic light system. Green means it was successful, yellow means it was successful with exceptions, red means that the test failed. Assuming that we've got all green, we can then deploy it to our physical arena of test robotic devices, which are able to stream the results back to Amazon S3, where we're able to continue to get those results in our business intelligence tool. And if all that is successful, and this could be a fully automated process right up to this stage, you'd probably want to gate it from here to determine if you've got all green, deploy it out into the field of physical robotic devices. Now, an organization that is doing exactly this is iRobot. So as you could imagine, iRobot have a considerable number of devices in the field, over 1 million devices in the field. They are best known for their robot vacuum cleaners. There are many models of the robot vacuum cleaners. As you could imagine, there's many floor layouts that those robot vacuum cleaners need to operate on. So late bug discovery is bad. When you've got that many devices, you certainly want to avoid late bug discovery. Testing is imperative. And testing can take a considerable amount of time if you're doing it manually, if you're sitting there watching a bunch of simulations. So iRobot looked to automate this using that CI/CD pipeline that you saw before to be able to automate the regression testing of their robotic devices.
AWS RoboMaker is the most complete cloud solution for developers to build, test, and deploy robotics applications at scale, giving companies the freedom to focus on designing innovative robots for their customers. Chris Kruger, the Director of Software Engineering at iRobot, knows this better than anyone.
iRobot was started in 1990. It's had some of the most innovative robots in the world.
Because of its expansive growth, iRobot needed better tools and infrastructure to quickly build and test their new software.
Our products are now expected to navigate through people's houses for up to 30 days at a time without any assistance. Our code base has grown tremendously. It still takes about 6 weeks to get software from our release out into production. And this is where simulation at scale can help us.
Testing software updates on physical hardware is time-consuming and resource-intensive. RoboMaker virtually replicates physical environments using industry-standard simulators based on conditions and behaviors robots have previously encountered.
Once we've got a stable and reliable environment, then we start to see the benefits of simulation at scale, where we can concurrently run all of our products and get feedback immediately across our product line on code changes.
Run hundreds of parallel simulations with a single API call, producing results in a fraction of the time it would take with physical robots.
It only took us a couple of weeks to get our Roomba code up and running in RoboMaker, along with our internal tools.
AWS RoboMaker allows developers to focus on experimenting with new code by running a fully automated continuous integration and deployment pipeline created with standardized infrastructure. Build higher quality and scalable robotics applications faster and with fewer resources. Learn more about AWS RoboMaker today.
So that gives you an idea of how another organization other than Amazon were able to use the cloud to be able to scale out capability to millions of devices. Now, when it comes to deploying and updating, so let's say that we built out a component, we've tested it out, regression tested it. We still need to be able to deploy it to our devices over the air in a stable and safe manner. If you're iRobot, you definitely don't want to be doing a deployment across all devices in one big hit. You want to be staging that. To be able to do that sort of thing, we are looking at usually a 3-tier IoT architecture when it comes to communicating with our end devices over the air. The first one is analytics services. So how can I make sense of my IoT data and take appropriate action? So you want to be able to assess telemetry as it comes in. So let's say that maybe the battery life is getting a bit low. If it is, be able to take the appropriate action, which is to redock that robotic device. Connectivity and control. How can I manage, control, manage, and secure my devices at scale? So if the battery device is running a bit low, how can I communicate with that robotic device to tell it to go back and dock? And then device software. So once I've sent that payload to the device, how do I then get that device to take action based on that payload? So for connectivity and control, what we're looking for is effectively a message broker that is able to communicate using industry standard protocols like MQTT to be able to receive telemetry and take action appropriately. For that, we've got AWS IoT Core, which is able to provide a message brokering system that is highly scalable, that is durable out of the box. You don't have to roll your own Mosquito brokers. And it supports, additionally, on top of MQTT, HTTPS, and even LoRaWAN. So it performs it uses X509 certificates for authentication, and all traffic is encrypted in transit. So it can communicate over 5G, over the internet, over Wi-Fi. And so it uses a pub-sub method, very similar to what we'd be used to in ROS, speaking to ROS topics. But one of the other things that IoT Core provides is the ability to communicate with devices that have intermittent connectivity through what are called device shadows. So if you have a device that may have intermittent connectivity, maybe you've got a front end that needs to be able to query that device to understand its last known good state, chances are that if your front end tries to connect to your back end constantly to pull that information, it's going to fail a lot of the time if you've got intermittent connectivity. So what you want to do is use something like device shadows, where your device is continuously publishing its last known good state to a shadow, and then your front end can pull information from that shadow as needed, so that you're not waiting on your robotic device to reestablish connectivity. It can go back the other way as well. So if you wanted to send a new waypoint to your robotic device, being able to publish that to a device shadow, which is then able to, when the device comes back online, determine that that device shadow has changed, and then be able to action that appropriately. Oh, there we go. And then rules engine. So basically being able to, what we can do with the rules engine on top of IoT Core is, as telemetry starts to stream in, we can actually run SQL queries across all of that telemetry and take appropriate action. So if you think of maybe a hospital robot that is navigating wards, it's seen someone that maybe has fallen over, it sends a telemetry payload that indicates incident equals true. We can be running a continuous SQL statement over all the telemetry that comes in that picks that up, run some appropriate code to get a nurse to come straight to that person. And so for edge-based software, to be able to communicate with our message broker and additionally run software over the air, we have AWS IoT Greengrass, which is an open source runtime engine, which is able to communicate with our message broker, but additionally it's able to run what are called components. Components are effectively modular bits of software that can be either a ROS package, it could be a Docker container that we're registering with Greengrass's cloud service. We're then able to, from there, deploy that component down to our edge device, or multiple edge devices. And then that edge device, Greengrass that's running on that edge device, will manage the life cycle of that component. So it sort of looks something like this, where we've got an IoT Greengrass cloud service. Our components would be registered against that cloud service. They'd be version controlled appropriately. And then from there, we have our device. We've got, obviously, our operating system, which could be Linux, could be Windows. One thing to note here is that Greengrass requires at least 1 gigahertz of CPU and about 96 megs of RAM. So it's, that could be ARM, it could be x86. It won't be running on microcontrollers. There's free RTOS for that. But on top of the operating system, there's AWS IoT Greengrass client software, and then that manages the Greengrass components. So any software you deploy down to that edge device will be managed by Greengrass. It will manage, if the component fails, it'll try to restart. It'll notify you appropriately. There are pre-built components that you can also leverage with Greengrass. So obviously you can create your own components and deploy them down to the robotic device. But you can leverage existing out-of-the-box ones as well that allow you to straight away package up a machine learning model and deploy it down to your device. Things like being able to use Kinesis video streams, as I mentioned before, the video streaming capability, to be able to deploy that down to the robotic device out of the box and be able to start streaming straight away. And then secure tunnels. This one's probably my favorite. So if you've got a device in the field, maybe it's communicating over 5G, maybe you think it's faulted for some reason, you go get some logs off it because you're not streaming them back. You can establish a secure SSH session through a Greengrass component to be able to land on the device in the field and be able to start troubleshooting. And so Greengrass over-the-air software updates for components provides a number of capabilities to ensure you're not sort of doing a big bang approach. So being able to do a configurable deployment rate and failure thresholds to be able to roll out your update across your fleet in a staged manner rather than a big bang, and then being able to determine the failure rates to be able to halt the deployment if you start to see failure rates start to rise. Obviously, you don't want to brick every device in the field, so being able to control that. Component rollback should a component deployment fail, and conditional update workflows. You obviously don't want to be pushing out software to a device that is currently performing a task. And so putting that all together, this is sort of what it would look like from an architectural perspective. So, a CI/CD pipeline to be able to build components, to be able to test that out before registering those components as potential Greengrass cloud services, as components within the Greengrass cloud service, being able to deploy those to production fleets, which then allow them to be able to communicate with cloud-based services, whether that's machine learning services or video stream capabilities, and being able to view all that from a front end. So an organization that is doing a lot of that today is actually ST Engineering, Singapore's own. So they have built out a fleet management system capability on AWS for their robotics as a service platform. They have been able to leverage things like being able to build robotic software and be able to register those as Greengrass components, be able to push those components down to their devices, be able to manage their devices at scale using IoT Core and Greengrass, being able to get video feeds back into the cloud or back to their web front end using Kinesis video streams, and then being able to use machine learning capabilities in the cloud for inference. So that sort of takes me to the end of the presentation. One thing that I did want to say is I started my career about 20 years ago, and 20 years ago, I'd say that for someone who, I've always loved technology, I've always loved being hands-on with technology, experimenting and prototyping. And 20 years ago was a hard time to experiment and prototype because most of the technology that you wanted to be able to use was typically out of reach. It was too expensive. You had to work for an organization with fairly deep pockets, and then you had to work your way into a specific part of the organization to be able to get your hands on that sort of technology. So we're definitely sitting in a different time now where a lot of the best-in-breed technology is available to you to be able to leverage. Cloud computing is a pretty good example of that, where you're able to sign up, you're able to get started, and a lot of what you use doesn't really even pass the free tier. So it's effectively you're paying for how much you use, and how much you use is negligible as a single person that has got an idea that's prototyping and experimenting. So I really do think it is the day one for very much for emerging technologies, cloud computing and robotics.
It's one small step for man, one giant leap for mankind.
Thank you.
I have a question about overall approach. Is it highly dependent on connection to your web services?
Sorry, which approach?
Sorry, not like approach. All of the pipeline that you are sharing with us, it basically, as I understand, highly depends on the constant online of all of the devices. Most of the customers for us has at least some kind of restriction to the outside networks.
Yep.
So I'm not talking here about continuous development or updating these kind of devices. It's obviously not possible because they are out of reach.
Yep.
But if I cannot leverage on some of the products, some of the parts of this approach, well, what can I do in these kind of cases?
Yeah, no, definitely. So look, I think there's still a lot of things that can be leveraged from a cloud computing perspective if communication is restricted. So for instance, the ability to still build intelligent capabilities for robotic devices. So being able to train machine learning models and deploy them down to the edge. I will say that a lot of what I showcased is very much the AWS way to do it. It doesn't necessarily mean that you can't swap and change things. So, even like the pipeline had, code pipeline, code build, code all the AWS. There's nothing actually stopping you from swapping and changing bits and pieces out because everything is effectively API driven. So, being able to leverage Jenkins or Bitbucket or Bamboo Server or, you can quite easily swap and change bits and pieces out. But when it comes to devices that are fairly restricted, that don't have the ability to communicate outside of the network, I'd say that you're probably, out of most of the things that we talked about today, certainly you could still build a pipeline offline and have that operating within your own environment, just wouldn't necessarily use any AWS services. But it would be probably more from a building intelligent applications capability. So potentially building a model, then taking that model and deploying it down to the device, not necessarily using Greengrass to deploy down to that device, but effectively copying it down to your network and deploying it to your device manually. So there's still a few things that you could definitely use, but I'd say, connectivity to things like a message broker in the cloud, probably out of scope.
All right. I think we have one up there.
Yeah. Hi. Morning, Bobby. Timothy here from ROS-I. I'd like to ask a question. So how would we see the impact of foundational models on two areas? The current workflow that you've just presented, also on the cloud deployments and the impact that we'll see or we expect to see. Yeah.
Yep. So it's a bit of an open question. So around, I still think in terms of integration with robotic devices, it's still fairly early days from what I've seen personally. So I can't comment from a practical standpoint. From a theoretical standpoint, there's still going to be, in terms of being able to leverage a large language model, for instance, in the cloud, it would be very similar to some of the architectural examples that I've displayed, where you'll still be able to interact with an API in the cloud to be able to perform inference. So there's still a latency aspect, but ultimately, if you want to be able to ensure that with your compute footprint at the edge, you want to ensure that you're able to run economically, then I would imagine that you're still running models, fairly large models in the cloud, still running inference over the wire to an API.